important. It's important. Well, it's important that you feel confident. It takes a while to learn all that stuff. That's why we have permits for so long. But that's good. Good for her. I'm happy for her. Y'all will all like that better. I'm sure your dad will too. It'll be like one less thing he has to do, right?
Yep, he has a lot of work.
Yeah, I'm sure. And it probably gets to be a lot for him to have to drive y'all everywhere you need to be. Well, that's good. It's great news. That is great news. Are you guys thinking when you turn 16, you're going to be excited about driving or scared about driving?
Both.
Both. So,
My sister is taking the driving test.
When does Cameron take her test? You don't know? Soon though? Your mom's life is about to change. It's scary when your teenager drives off for the first time without you, but it's great because it's like, But out of the two boys, like Cole got in a car and it was like an extension of him, like immediately, like he'd always been there. Drew took a little longer to adjust to it, but Cole's like, of course, this is Cole. Cole comes home. I got a new minivan, right? Like right before Christmas. So when Cole came home for Christmas, he's like, can I drive it? Can I drive it? And I said, well, hold on, let me go with you. It's got a bunch of like features and stuff that you probably aren't used to. You don't have in your car, right? So let me show you. Let's go together. So he gets in my van, and all we did was just drive kind of around here. But it was like being on a racetrack. Like I was holding on because he really wanted to feel it out. So he's whipping my minigun around corners. Because that's how he drives. He's got a low to the ground sports car. So I mean, he's got a Chrysler 300 that he has pimped out to a certain degree. So like he had the windows tinted for Christmas. That's what I got him for Christmas last year. And he's done a chrome delete. So anywhere there was chrome is now black. Yeah, you may have to shift an inch or two. I can't fix that one. Like I put down these blinds, but I can't fix that one up there. But yeah, and then he switched out the tires. That was one of the first things he did. He took the stock tires off and put on like big fat tall tires on the back and then like taller tires on the front. Yeah, no. So being a dude who loves his car. And then Friday before last, so you have to picture this. This is a 19-year-old kid whose favorite thing on the planet is his car. Okay, that is his baby. It is always neat. If people get out and put their hand on the door like this to close it, I have seen him go around and take his shirt and wipe the fingerprints off because you didn't use the hand. Like I'm not kidding. It's always pristine. It's always perfect. He's changed the exhaust system. He changed the tires. He's in the chrome delete. Like he's done all, it's his baby. It's his baby. And it goes boom, it makes this terrible noise. It's not even a good pitch. But anyway, he was sick. He got the flu. And on Thursday, he gone to CVS and gotten some more medicine. And then he still had a little fever. So he was like doing the thing where you rotate Tylenol, ibuprofen, and he had Tylenol in the car. So he left his apartment. He lives in an apartment in Waco and he has a parking garage. So he goes out to the parking garage to get the Tylenol and his car's gone. Gone. I cannot imagine the level of panic. Turns out he had failed to renew his parking pass. They'd been sending him emails and he didn't see them because he wasn't checking that email account. That's on him. And he failed to renew his parking pass, so they towed it. But he thought it was stolen. So he was in absolute panic mode. So we went to the front desk to talk to them and they were all like, oh yeah, it was probably towed, call this number. And of course it had been towed. Do you know how much it cost us to get his car out? $330 to get his car out. $330.
And let me guess, he begged.
Well, he didn't have a choice because he doesn't have any money because he doesn't have a job right now. And he spent all of his money he earned in the summer, and we send him an allowance that has money in it for him to have fun with, plus money for groceries and things like that. But there's enough for him to go do that. We don't want him to go to college and not do anything because he has money. Like, go do things. But he spends a lot. So he didn't have any money, so he had to text us and he's like, hey, just so you know, I'm about to put $330 on the American Express. And Jason immediately called him and he's like, no, you're gonna ask me if you can put that on the American Express. He's like, my car got towed. Okay, are you serious? Are you serious with this? Like, He said, well, they sent me a couple of emails, but they went to my Gmail and not my BearWeb. BearWeb's his college school account, and that was what he was checking, not his email, his Gmail account. Check your email. Check your email. He missed it and off away with the car. All right. Are we ready, folks? So everybody's got their Q4 packets. Very good, very good. I know we usually don't meet when public school is off, and apparently they're off today in Forsyth, but this was one of those that if I took out this week and let you have today off because they had off, then in order for us to end at the right time, I would have had to take away an entire day of final exam review, and I wanted you to have the day of exam review. So here we are. And you probably want the day of exam review too, don't you? All right, so we are doing a little more about acids, bases, and solutions today. Acids and bases in solution. So we're talking typically about aqueous solutions of acids or bases. Why is my phone going off? Y'all stop texting. So, hey, good morning.
We're having drama here.
Oh,
As you know, probably they have freshly pierced
yes,
ears.
ears.
And I knocked this out
Uh-oh.
while putting, do you happen to have an extra bag?
I might can y'all give me 1 second? Okay.
I'm so
Let me-
sorry.
Is it the
Or
screen?
an eraser? No, it just,
Feed us too,
Yeah.
it's okay. I might, let me
even
look.
if you just have an eraser.
Actually,
that
I
can
do
cut.
have erasers, because here's my thing, I'm like super allergic to nickel, so all the backs I have are gonna be gold or
Okay.
platinum, so.
Okay.
That's a big old eraser, but
Should
you
I
want to break
cut
it
it?
and hang on, let me see, I have a blade.
Yes.
Because even those are like, even the gold ones sometimes bug me, so now I have some new acrylic ones. That I haven't tried them.
Sorry, all this is.
No. Oh, there, this is my.
Cause you know, I don't wanna leave it out all day.
No, you don't.
Yeah.
Do you
Yeah,
hear?
getting my ear back in.
I'm not gonna do that.
Did you do it with the gun or with the needle?
Needle.
Yeah,
Yeah, we put
it's a little slower sometimes, but it's a better way to do it.
yeah.
All right, here's a, here,
Okay.
I'm just gonna fix all that. You
All
wanna go to the bathroom or whatever works? Let me tuck this half an eraser back in this pen. I think it'll work. Looks like it never happened. All right. So we'll go ahead and start. She'll be in a minute. All right, so acids and bases in solution. Let's see. All right, let's see what we remember. Acid neutralizes what?
Neutralize ions.
No, you know? When you put an acid with what, it goes neutral. Base, an alkali or a base. Remember, an alkali is a base in aqueous solution. So acid, we're talking about acids and bases in solution. So an acid neutralizes a base.
I'm so sorry about that.
You're fine. Hey, look, there's your Q4. Do you want to take it or do you want to give it to your mom before she goes out the door? There you go. So if acids neutralize bases, bases neutralize Emerson. Atta girl. Okay. So acids can dissolve some metals. Base is slippery. And acids you can say are sticky. Okay, acids turn litmus paper what? Red, she says, and she is right. Now, I'm going to show you. This is blue litmus paper that I dipped in acid this morning. This is all that's left of the blue because the acid wicked its way through the paper. So this is how it started, and that's how it ended. And you have some today in your lab bins just for heck of it, if you wanted to do it. And then what's the next one? Bases turn your litmus paper, Emerson? Blue, and here's one of those. So here is, this was the red litmus paper, and that's where I dipped it in the base. And you can even see where a little drop, you see where the little drop got on the end of it? You see it? Yep. So that was red litmus paper, and the easy way to remember that is base turns blue. Base turns blue, and then you can remember. So how do acids taste, Everly? Sour. And how do bases taste, Eunice? Bitter. Very good. A molecule or other entity that can donate what? What do they do? What do acids donate, Annabelle? Do you remember?
Protons.
Yeah. So they donate a proton or accept an electron pair in reactions. Very good. And then a molecule or other entity that can accept a proton or donate. What kind of ion?
Hydroxide.
An electron is what we're looking for. Okay, so acids can donate a proton or accept an electron. Bases can accept a proton or donate an electron. Okay, and remember, the easiest way to kind of remember about the charges for acids and bases is to think about how you have sorry, how you have with water. If you were to break water into its constituent parts to get acid and a base, you would get like an H plus, and then you would get an OH negative. Anything that ends in an OH negative is hydroxide. Anything that ends in hydroxide is going to be a base. Today you're using sodium hydroxide in lab. So a hydroxide is a base, an OH negative, and an H plus is going to be your hydrogen. So that's your acid. Okay, Everly, what's a pH for an acid? Oh, was that what you were going to answer? No. Okay. Oh, what's your question? What happens with the base in blue litmus paper? So this is an indicator. So that's what you're going to be using in lab today. I'm going to show you a couple different kinds of indicators. Indicators will typically show a color change in the presence of an acid or a base. There's a chemical reaction, obviously, that takes place, right? Because that is, a color change is a sign of a chemical reaction. And it's different depending on what the specific indicator is. And I'm not positive of exactly even what it is for a litmus paper, like the whole chemical reaction. But it lets you know that a color change, when a color change has occurred, it lets you know that which way the pH is. So today in lab, I'm going to, before we start lab, I'm going to show you, like right here, I have 3 clear, see the, whoop, almost dropped that. You see that? One of these is distilled water. One of these is sodium hydroxide in water, which is a what? Acid or base? Hydroxide, base. And the other is, I don't remember if I put in the sulfuric acid or the hydrochloric acid, but it's one of those acids, okay? And when we put in universal indicator, which is orange on its own like this, see it? When you put universal indicator in, there's a spectrum of color that'll tell you where the pH goes. We're going to do that before lab just to watch. And then the fun one is, and I'm going to borrow, actually, I need 2 volunteers. Let me pick them now. Who wants to volunteer for something? Lucy. I'll do Lucy and Emerson because their hands went up first. So not now, but when lab comes, I have 2 flasks that look like blue, just blue liquid, right?
Yeah.
One of them has water and food coloring in it. The other has water, bromothymol blue, which is this guy right here, which looks kind of green in there, and a tiny bit of either an acid or a base. And bromothymol blue changes color in the presence of acid or base. And the way we're going to make it work is you're going to take straws and you're going to gently blow bubbles into these. And one of them will change color, because when you add carbon dioxide to water, you produce some carbonic acid, and as it becomes more acidic, you'll see a color change. And it's really kind of fun. Like it changes color right before your eyes, which is really kind of neat. All right, so acids have a pH of what compared to 7? Annabelle? Less. And then bases are, Everly? Bases have a pH of more than 7. Yep, okay. A chemical substance, usually a liquid, which contains what and can react with a base to form salts. What's this going to be? Usually containing what? Do you know?
Water.
Well, hydrogen. Remember our H plus, our little proton, and then a substance which contains what's going to be in the bases then? Hydroxide. That's right. Okay, acids have a hydrogen, bases have a hydroxide. So today, for example, you're using hydrochloric acid and sulfuric acid, but the formula for sulfuric acid is H2SO4, so there's your hydrogen right there, right? And then your sodium hydroxide is NaOH. There's your OH, that's your hydroxide. OH, H plus versus OH negative. All right, let's watch this quick little TEDx on acids and bases. TED-Ed, not TEDx, TED-Ed. If it'll go, here it goes. And I'm sure we have a commercial because we have commercials everywhere now. Yay, school day, snow day, snow day. We don't get snow days. We're homeschoolers. We don't even know what that looks like. All right, here we go.
Acids and bases are everywhere. They're used to make foods, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides, even paper. Our stomachs are very acidic. Our blood is slightly basic. Our proteins are made up of amino acids, and the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules, acids and bases were defined by how they behaved. Acids tasted sour and corroded metals. Bases felt slippery and could somehow counteract acids. When molecules dissolved in water interact, they're exchanging two main currencies with their surroundings: protons, also known as hydrogen ions, and electrons. Depending on how a molecule is composed or shaped, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has two protons, but is generous enough to hang out with just one. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules has exchanged currency with water. As you might guess, we label these acids and bases weak, but in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, that is a weak base. So it doesn't take much to be an active player in the chemical economy. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And when a proton deposit customer, that's an acid, and a proton withdrawal customer, the base, shop at the same time, their net effect on water's account may cancel out, and we call this neutralization. Now, certain molecules can behave as acids or bases without water, but that's another story. Let's end by saluting water as the resilient and fair banker for acids and bases. It's always open for business, doesn't charge interest, and will never foreclose on your molecules, which is more than I can say for wah wah.
All right, so this is something important to understand. Water will disassociate on its own. Remember, I was saying a minute ago that your water has your hydrogen and then it has a hydroxide. If you were to break it apart, right? You could break one of the hydrogens off and you'll have an H+ ion, and then you'll have hydroxide, which is negatively charged. So water will disassociate or break up like that on its own, but it doesn't do it very often. So basically what you get here, it says yellow and red. I don't know why it says yellow and red, because they're not yellow and red, but you can get a water molecule to break down into your negative OH and your H+. Or you can put them together, and you can take one of these little H+ can join a water molecule, and then you get something called hydronium.
Things where someone sees something and someone else sees something else.
Oh yeah?
Maybe the person that created it
Maybe.
saw yellow and red.
Or maybe I put those colors in and didn't see it. I don't even remember. But, so yeah, so what you got there is you have, remember, water looks like Mickey Mouse, right? You got your water and it can break apart into the hydroxide and the hydrogen ion. So you can get both the hydroxide ion and the hydrogen ion, OH negative and H plus. This guy is going to be basic and this guy is going to be acidic, right? Now, if you put them together, one of these random H plus that's bouncing around can join your water molecule and then create H3O, which is hydronium. So that can happen all on its own without you having to do anything. Yes.
What is H4O?
I don't think there is an H4O actually. So somebody tell me about strong acids. What do you have for, yeah,
Stomach juice.
that's one. Yeah. What are the qualities of a strong acid? Do you know?
They can break up or rust metal very easily.
They can, yeah. So in an aqueous solution, a strong acid will react completely with the water and it's going to produce, what's this guy right here? Your H3O, hydronium. Okay. So if you put a strong acid in water, think about it. You have those H pluses floating around because it's a strong acid. Enough of those are going to come in contact with H2Os and they're going to form H3Os. So you can get hydronium. Weak acids are going to disassociate only partially in the water. So this is your weak acid right here. Here's your hydrochloric. It can be weak or strong depending on it, but it's not like, I mean, there are worse ones. But anyway, you can see how it breaks down and then how you could take this little, actually, sorry, this is your strong acid. I'm sorry. The hydrochloric is pretty strong acid usually, unless it's dilute. Like we are using it today, but we're using only a 0.1 molar. So it's very dilute. Whereas last week, do you remember we used drops of hydrochloric acid and I was like, be careful. Yeah. So see how this one has disassociated into a chloride ion and a hydrogen ion. And that hydrogen ion is going to join with the H2O and make hydronium ions. So it's a stronger acid right there. So when you work with HCl, it will typically be in an aqueous solution. Usually we have liquid HCl when we're working with it, right? Strong bases in an aqueous solution react completely with the water to produce H negative hydroxide. That should say OH negative. Whoop! I have to fix that. What is that about? Hold on, I'm going to fix that because that is not good. There we go. They produce your OH negative. All right. There we go. Which is your hydroxide ion. And then your weak bases disassociate only partially in water. So here is your sodium hydroxide, which is what we're going to use today in lab, is a strong base. And it's going to disassociate into a positive sodium ion and a negative hydroxide ion. And then you get this hydroxide ion here. But what's going on here? What's this about? Where'd that come from? Where do you think that came from?
Came from random.
This would come from the water that automatically and without you doing anything will disassociate on its own. And that water will have some free hydrogen floating about in it and it will find that hydroxide ion and then it will make more water. So that can happen. All right, now we have something called Bronsted-Lowry classification. There are different ways to classify acids and bases. There are different ways to describe acids and bases. But Bronsted-Lowry classification specifically deals with protons. So a Bronsted-Lowry acid is going to donate what? Going to donate protons. That's what we want. A Bronsted-Lowry acid right here is going to donate a proton. And a Bronsted-Lowry base is going to accept what, Annabelle?
Electron.
It's going to accept protons because Bronsted-Lowry classification is only concerned with protons. So bases acids donate, bases accept.
Oh.
Acids take them on, bases accept them. So that's how Bronsted-Lowry is classified. So here you have an acid and it shows you like, here's your little, there's your negative, right? And there's your negative over here. Here's your pluses, right? So acids are proton donors, bases are proton acceptors. And it makes sense because this guy could use a proton to make itself neutral. If you added this H plus to this OH negative, what would you get? Neutral what? What compound would you have if you added that H plus to the OH negative?
Ion.
Think about it. You have a hydrogen ion and a hydroxide ion. If you put them together, what happens? Water, which is neutral, right? So that neutral water is what happens if you put your acid and your base together. Water is going to form and it's going to be neutral pH. So these guys are donating the H plus to the OH negative, which is going to accept it. That's how Bronsted-Lowry classifies. Okay, so now let's talk about acids, bases, salts, and pH level. Yes, we know. Snow day, snow day. Yeah.
Acids, bases, salts, and pH level. Acids, bases, and salts are inorganic substances that break up or dissociate in solution or water to form charged particles or ions. The positive ions are called cations, and the negatively charged ions are called anions. Before we look at acids, bases, and salts, let's take a look at water. A water molecule is made up of an oxygen atom and two hydrogen atoms that are covalently bonded or share electrons with the oxygen atom. However, the electrons are not shared equally within the molecule, as they have a higher probability of being found closer to the nucleus of the oxygen atom, giving that end a slightly negative charge. So the hydrogen atom's end of the molecule will have a slightly positive charge. These charge ends weakly attach the positive end of one water molecule to the negative end of an adjacent water molecule. This attraction or bonding is called a hydrogen bond. Sometimes this attraction of a hydrogen atom of one water molecule to another molecule becomes so strong that it actually detaches from its original molecule and attaches to the other water molecule. So this yields a hydronium or H3O positive ion and a hydroxide or OH negative ion. Also, water molecules continually dissociate to form positive hydrogen ions and negative hydroxide ions. This is a reversible reaction as noted by the formula H2O double arrow or reversible reaction, positive hydrogen ion and negative hydroxide ion. The actual amount of these positive H3O or hydrogen ions in water is actually very, very small. To make things easier to understand, we will consider the positive H3O ion and the positive hydrogen ion as one and the same. So in pure water, the amount of positive hydrogen ions and negative OH ions is the same. Now for acids. An acid is any substance that when added to an aqueous solution or water will release a hydrogen ion or increase the concentration of hydrogen ions. So how strong an acid is depends on the amount of hydrogen ions produced. For instance, hydrochloric acid or HCl, which is a hydrogen atom bonded to a chlorine atom, when added to solution or water, will dissociate or break down into negative chlorine ions and positive hydrogen ions. Hydrochloric acid is a strong acid as it completely dissociates in water. Now for bases. Bases are essentially the opposites of acids in that they shift the hydrogen ion, hydroxide ion balance in favor of the negative hydroxide ion. This can be done by increasing the number of hydroxide ions or decreasing the number of hydrogen ions. For instance, sodium hydroxide or NaOH will break down or dissociate into positive Na ions and negative OH ions. So the balance is shifted in favor of the negative hydroxide ions, meaning sodium hydroxide is a base. Bases can also be strong or weak, depending on how well they break apart. Sodium hydroxide is a strong base. This brings us next to the pH scale, which is basically an abbreviation for the phrase power of hydrogen.
Maybe.
So the pH
That's
scale
arguable.
measures the concentration of hydrogen ions of a solution, or it measures how acidic or basic a substance is. As the amount of positive hydrogen ions increases, the pH goes down and the solution becomes more acidic. As the amount of positive hydrogen ions decreases, the pH goes up and the solution becomes more basic. On a pH scale, a pH of 7 means the solution is neutral, or the number of positive hydrogen ions equals the number of negative hydroxide or OH ions. A pH of less than 7 means the solution is more acidic, or more hydrogen ions than hydroxide ions. And a pH of greater than 7 means the solution is more basic, or more hydroxide ions than hydrogen ions. On the scale, hydrochloric acid, which we mentioned earlier, and is produced in the stomach, is at the most acidic end, having a pH of 0. Vinegar has a pH of 3, coffee has a pH of 5, and pure water has a pH of 7, making it neutral. On the opposite end, sodium hydroxide, which we mentioned earlier, is at the most basic or alkaline end, having a pH of 14. Ammonia has a pH of about 11, and baking soda has a pH of between 8 and 9. Now we can look at salts. A salt is a chemical compound formed from the reaction of an acid with a base. So hydrochloric acid, HCl, can interact with sodium hydroxide, NaOH, a base, and form sodium chloride, NaCl,
And you're gonna
and
do that in lab.
H2O. Salts break
And you
apart
did it
or
last week, too.
dissociate in a solution of water to form positive and negative ions, which make them important for certain body functions. There are many different salts that are important in the body, such as sodium chloride, or NaCl, and potassium chloride, or KCl. These salts are often most effective as charged ions or atoms in solution, as a positively charged potassium ion and the positively charged sodium ion are required for muscle contraction. And that be the basics on acids, bases, salts, and
So your acids and bases, when they neutralize, are gonna produce salt and water. Sometimes a gas as well.
Say potassium, I heard him say potatoes.
Potatoes. Yeah. So you need, there's sodium, they're called sodium potassium channels, and those are what function in your neurological system, where your musculoskeletal and neurological system interact. So if you don't have sodium or potassium in your body, your muscles don't work. Yeah.
I have a science show.
Okay.
What do you get when a sodium atom is next to a hydrogen atom?
A sodium next to a hydrogen. What?
Now,
There you go. So if you look right here, we have basic and acidic. All right. Now, this is an important question. Let's see. Why do you think a toothpaste is more basic? We make toothpaste, right? It's not in nature. We make it. Why are we making it intentionally basic? Why do you think?
Yeah.
It has to go in your mouth. But look, you can put black coffee in your mouth, and that's a 5.
and you can put.
And you can have vinegar and cola and stuff, and that's a 3.
And you can
It just doesn't taste good.
So you can eat some of these look at that. You can eat vinegar, right? That's a 3. And that doesn't bother you. And but toothpaste. So what's the pH of saliva generally? Do we know? Is it more acidic or basic? It's acidic. Saliva is acidic. It helps break down food when it gets into your mouth, and it's acidic. And your saliva, when it's combined with sugar, makes now you've got holes in your teeth, right? Some people have naturally more acidic saliva. You know how you know if you have naturally more acidic saliva? If you've got nice, healthy teeth with good enamel and you brush them a lot and you don't have a lot of buildup and yuck on your teeth, but you still get cavities, this is me. You naturally have more acidic saliva. So toothpaste is going to neutralize some of that saliva so your teeth don't get eaten up by your own saliva. Because for some of us, that's what happens. It doesn't matter how good of care I take of my teeth, they still get holes in them.
Can you test your pH of your saliva?
Sure, you could. You absolutely could. And that's the thing, is it's a very weak acid, your saliva, but at the same time, exposure over a really, really, really long time can still make holes in your teeth. So you can see here that as pH increases, pOH, like here's pH is decreasing, pOH is increasing. pOH is just the flip opposite of pH. So if you look right here, pH, pOH. See how the numbers are reversed? Typically, we just use pH, but you can use pOH too. And when you use pOH, you get the opposite. So H plus is the concentration of hydrogen ions is pH, and the concentration of hydroxide ions is
POH, right? So he said power of hydrogen, and that's arguable. It may not be power of hydrogen. It may be what's also called potential hydrogen. So, but what does pH mean? Where did it come from? Okay, I asked this type of question. The question I asked is, where does pi come from? 3.14 pi that you use in geometry? That's the one. And it ended up reducing my pre-algebra student teacher, Miss Prisborowski, to slobbering tears, and I felt like dirt. I did. I wanted to know where they got pi from. I said, what is pi? She said it's 3.14. And I was like, well, what is it? So she wrote out more of the number. And I'm like, no, I'm not asking. You can't pull a number out of thin air.
This is your actual teacher?
It was a student teacher. Yeah. So she was learning to be a teacher. But I wanted to know where the number came from. Like, you can't just pull a number out of thin air and have it magically work. It has to come from somewhere, right? It didn't go well because she ended up crying, and I felt really bad because I did not ever want to make a teacher cry. I was like a good kid. I never got in trouble. I felt terrible, but she couldn't answer my question. And it has to do a lot with circles and angles and triangles and things of that sort. But I still don't know that I completely understand. But this is that type of question. So it comes from this dude, SPL Sorensen. Whenever you see that little O, you know that's somebody that's like Nordic, right? Like Swedish or maybe Norwegian, that name. And he invented the pH scale. So the exact meaning of P in pH is disputed, as Sorensen did not explain why he used it. Thanks, dude. Thank you for giving us something that we are forever going to wonder about because you didn't explain it. He describes a way of measuring it to use potential differences, as it represents a negative power of 10 in the concentration of hydrogen ions. All the words for these start with P in French, German, Danish, all languages that Sorensen published in. So in Carlsberg Laboratory, where he worked, was French speaking. German was the dominant language of scientific publishing, and Sorensen was Danish. Remember I said he's probably Nordic? There you go. He used Q in much the same way elsewhere in the paper. So P could stand for puissance, or German potens, or Danish potens, meaning power, or it could mean potential. He might also have just labeled the solution P and the reference solution Q arbitrarily. And these letters are often paired, which is great fun if you're dyslexic, because P and Q are like just flips of each other, right? There is little to support the suggestion that pH stands for the Latin term pondus hydrogeni, which is quantity of hydrogen, or potentia hydrogeni, which is power of hydrogen. So currently in chemistry, the P stands for decimal co-algorithm of. Oh, that's fun. And it's used in a term pKa for acid dissociation constants, and POH, and the equivalent for hydroxide ions. So now we consider P as meaning decimal co-algorithm of. Yes, Miss Lucy. I have. Yep. I'm not Sherry, but I did. I had a full psychoeducational analysis done after my first year of college, because despite having been in a gifted program all through high school, I failed a pre-calculus class because I'm really not good at math. And that's how I discovered I had learning disabilities. So pH, and I got all the way to 19 years old before anybody figured that out, which was not great. So here's pH and POH. Oh, and a hot tub. Ooh, I want that. There you go.
Our learning intention for this video is that we will understand pH and POH and what they're representing.
H, because she's British.
We can use pH.
I'm going to run to the
tell us
restroom real quick
how
while this
acidic
video runs.
or
Okay.
how alkaline a substance is. If you've missed my previous video on revising acids and bases and the pH scale from Stage 5 Science, I'll link it up in the top right-hand corner of this video for you. The pH of a solution is actually a measure of the concentration of hydrogen ions that are in the solution. A solution that has a high number of hydrogen ions, we say, is very acidic, and it will have a very low pH value. So a pH value that is less than 7 is said to be acidic. We can refer to pH as being the power of H, so power of hydrogen, or the potential of hydrogen. A solution with a high number of hydroxide ions, so that's our OH minus ions, is said to be basic and has a very high pH value, so something that is over 7, where 7 is neutral. We can calculate pH as it is defined as the negative logarithm of the hydrogen ion concentration of a solution. The pH scale is logarithmic, and as a result, each whole pH value below 7 is 10 times more acidic than the next higher value. So for example, a pH of 4 is 10 times more acidic than a pH of 5. And a pH of 4 is 100 times, so 10 times 10, more acidic than the pH of 6. And that is what we mean by logarithmic. Let me show you a couple of examples. We know that in pure water, the pH equals 7.
Actually, she's Australian, isn't she?
But
New
why
Zealand.
does it equal 7? So in pure water, the concentration of the hydronium ion or the H plus ions are equal to that of the hydroxide ions. And that concentration of each of those are equal to 10 to the power of -7. Now, if we substitute that into our logarithmic equation, so the minus log to the base 10 of whatever the hydrogen ion concentration is going to give us the pH. So if we sub this value in, then we get that the minus log equals 7. Now, if we do the same thing for the concentration of the hydroxide ions, we get the same value.
But you can
because
see
we're
how it
subbing
works.
in the same concentration because the concentrations are the same. Now, this also makes sense.
Now, this you're
because
not
we
gonna get
know
tested on, but I want you to
that
understand where the
the
numbers come from.
pH plus the pH
They actually mean something.
is going to equal 14.
So that's where that 14 comes from. It's not completely random. So let's real quick breeze through neutralization. So neutralization. Neutralization is when a base and an acid are mixed, the hydroxide ion and the base combine, I should say in the base, combined with the hydrogen ion from the acid to form water. And that process is called neutralization. Water and a salt. Base plus acid equals a salt, water and salt. So here's an example, hydrochloric acid, sodium hydroxide, when combined are going to produce water and sodium chloride. And that is right there. You can see there's where your water is coming from, right? And then you get a salt based on what other components exist in the water. All right. This one is quicker. I think this was the quicker one, but it's really cool. Oh no, this one was
Neutralization. By definition, it means to render something ineffective or harmless by applying an opposite force or effect. So it could mean to kill someone you really don't like, or it could mean when an acid and
Neutralize.
base react to create a neutral solution. Now, first you need to know some stuff about acids, bases, and neutralization. The definition of an acid is basically anything that donates a proton, so they contain the hydrogen ion, which has a positive charge. And a base is anything that accepts a proton, so they contain the hydroxide ion, which has a negative charge. And in chemistry, when something is neutral, it most of the time means something that has around a number 7 on the pH scale. And so an acid solution has a number smaller than 7, and an alkaline solution has a number bigger than 7. Some acids include hydrochloric acid, sulfuric acid, nitric acid, ethanoic acid, citric acid, and carbonic acid. And some alkalis include sodium hydroxide, potassium hydroxide, calcium hydroxide, and ammonia. Now, in neutralizations, if an acid and an alkali or base react, they make salt and water because the hydrogen ion from the acid combines with the hydroxide ions from the alkali to make 2 parts hydrogen and 1 part oxygen, which is water. But this is not always the case. There are neutralizations where acids react with a metal, which then also creates a salt, but then hydrogen and water. And an acid can also react with a carbonate to form salt, water, and carbon dioxide. Well,
Yes.
how does neutralization affect our everyday lives? Do they help us in any way? Well, in our everyday lives, we actually see pretty many neutralizations going on. Like when a bee stings on the skin, it produces a mixture of acidic venom and baking soda is applied on the skin for relief. Therefore, neutralization takes place. Wasp stings, on the other hand, is basic, as in it's alkaline, and vinegar is used for relief on wasp stings. When someone suffers from a heartburn, some antacids are given to eat so that neutralization can take place in the
You ever
stomach.
taken a Tums or a
Stomach
Rolaids?
has hydrochloric acid in it, whereas a popular antacid is milk of magnesia, which contains MgOH2. In energy industry, power stations burn fossil
What now?
fuels such as coal to produce electricity. The burning fossil fuels will liberate sulfur dioxide gas as an acidic pollutant in the air. Hence, power stations treat this acidic gas using powdered lime, CaO, or limestone, CaCO3, to neutralize it so that air pollution can be prevented. Other types of neutralizations in real life can be, when plants don't grow well in acidic soil. Lime fertilizers such as powdered lime, CaO, or limestone, CaCO3, or ashes of burnt wood are added to the soil to neutralize its acidity. Also, shampoos are mild alkaline, which causes small scales in each of our hairs, which makes our hair unmanageable, so rough. Hair conditioners are mildly acidic. When used, the acidity in the hair conditioner will neutralize the alkali in the shampoo and cause the scales to close up. So yeah, neutralization is something you can see in real life and not just some boring thing you learn in chemistry class. It can help you understand why and how a heartburn happens and how to treat it. Without knowing about neutralization, you wouldn't be able to make your hair silky after using shampoo. Pollution and acid rain would kill your trees in your garden, and you definitely wouldn't have cheap, plentiful, healthy food in the fields if it weren't for people figuring out neutralization.
Has anybody ever taken a Tums or anything for heartburn before? You ever had heartburn? Take a Tums?
So
They really work.
I take this like caramel
Mhm.
stuff
Yeah.
that after I finish eating a meal sometimes and
Uh-huh.
it helps my digestion.
Helps you digest, yep.
Yeah.
Mhm.
The sushi sometimes gives it to me really bad, but I love
Heartburn hurts.
it.
And it's not your heart. It's acid coming back up your esophagus. It's stomach acid coming back up. Sometimes, but usually just hurts really bad, like right here, which is why they call it heartburn. It burns and it hurts kind of in the center of your chest. So
It kind of hurts to get dog.
sometimes it does if it
Yeah, I
comes
got
all the way
that
up.
lots of
Mhm.
times.
It's gastroesophageal reflux is what it is. But yeah, one of my medications can make me get heartburn really bad. And one night it was the worst I've ever had. It woke me up in the middle of the night and it was so painful. I was like, am I having a heart attack? This is like really bad. So I ate about 12 Tums and it didn't make a difference. So I came down here and made a glass of warm water and tried to dissolve as much baking soda in it as I could, which by the way is gross. And I forced myself to drink it because it hurt so bad. It fixed it, but it was disgusting. I thought I was going to throw it up. Okay, let's go over your notes and your homework real quick before everybody else comes in. So these should be your answers. Substances with a pH in this range are acids, in this range are bases. In water, acids form hydrogen ions, and in water, bases form hydroxide ions, right?
Wait, so sometimes you have to throw up?
Well, everybody does at some point. We all do. Just what our bodies do sometimes. So what's the
Like because of heartburn.
Oh, sometimes. Well, it wasn't the heartburn. It was the taste of it was the baking soda. Okay, so difference between a strong acid and a weak acid. In a strong acid, most of the molecules break up into ions in solution. In a weak acid, fewer break up into ions. The strong base, weak base. In a strong base, most of the molecules break up into ions in solution. In a weak base, fewer break up into ions. So strong acids and bases ionize more efficiently. Yeah, because they dissociate more. So which solution has a greater concentration of hydrogen ions? One with a 3 or one with 7? One with 3 because it's lower on the pH scale, so it's more acidic, so it has more hydrogen. What are the products formed when an acid reacts? When a base reacts with an acid, you're going to get a water and a salt. And what is the pH of a neutral solution? 7, right? So your answers here are your hydrogen ion is H+, your pH scale is a series of numbers that indicates the concentration of hydrogen ions in solution. Your neutralization is a reaction between an acid and a base. Salt is the ionic compound that can form from a reaction of an acid and a base, and hydroxide ion is your OH negative. Use the reaction between hydrochloric acid and what? Potassium hydroxide to describe the neutralization reaction in terms of reactants, products, litmus paper. So that would look like this. HCl plus KOH yields KCl plus H2O. So potassium chloride and water. Your reactants and products are as shown, right? Actually, that's backwards. Why is that backwards? I gotta fix that. Sorry, those are backwards. Don't look at that. Identify types of compounds. Acid plus base yields salt plus water. You name the compounds as such. We already did. And it's going to turn litmus paper red and blue. And then there should be no change once it's neutralized. All right, y'all are good. So get everything out. These are backwards. I need to swap those around.
Oh, we're doing the acid base.
Yep. Yep, so you're gonna stay in here. I'm gonna bring everybody in here first. So y'all come on into the living room, okay? Don't go into the lab yet. We'll go in there in a minute. Come find a seat first before you go into the. So before you come in the kitchen, go find a seat over in the living room area first, or the breakfast room. We have to go over a few things before we start. I'm throwing pens. I don't know what, but I'm throwing. That's an old one. Where's that one in there? Yes.
Like a jawbone or something.
Oh, yeah. Oh, I have for you. That's from Annabelle.